Welcome to episode 4 of adding Houdini to your arsenal. Today I want to talk about clones, working with clones. Effects based on clones are quite popular, and in other packages like Maya with Mesh, Cinema 4D with MoGraph, or a Blender with animation nodes, there are systems to handle a lot of clones and to animate them easily. In Houdini there is no dedicated system to do that, but with Houdini's flexible tools it's very easy to build one. So follow me today while I show you how to build motion graphics effects in Houdini. To get started, lay down a GeoNode and call it clones. And dive inside. As always, get rid of the file sub. Instead we want to lay down a grid. And the grid is always too big, so make it smaller and up the subdivisions to 50 by 50, like so. In Houdini, working with clones works a little bit different than in other packages, because Houdini is not dealing with objects, it's dealing with geometry inside of one object. So it's replicating geometry. And to do this, it uses something it calls template points. And template points are nothing special, it's just any sort of point you have. And these points are used to tell Houdini where to put the copies of an original geometry. So if you create a box, for example, like so, you get a huge box. So append a transform node to make it smaller, like so, and let's say 0.01. Well, that's a little too small, maybe 0.02. Now I have a small box. And if I now want to replicate this box, I use the points of this grid to do that. And the node that I use to do it is the node called copy to points. It does what the name implies. It copies geometry to points. On the left side, it expects primitives to copy, and on the right side, target points. So connect the scaled box to the left side and the grid to the right side and makes the copy to points node visible. And you see you get a lot of cubes, a lot of boxes. You can turn off show guide geometry because I think it's a little bit distracting. And you see now you get a grid of individual boxes. If you go down with a scale, you get gaps between them. But be careful, because these are not objects, it's just primitives. So if you turn on primitive display, you see what we created is one big chunk of geometry that is composed of individual cube-like elements. But it's just one big piece of geometry. But this is actually a good thing, because it's a lot faster than dealing with individual objects. But to be honest, this is a little bit boring. We want to do stuff with our individual clones. And we can do stuff to them, not by influencing them directly, but instead by influencing the template points. So instead of appending stuff to the output of this node, which is all the individual faces, all this polygonal geometry, instead we want to alter the input points. If I, for example, use a mountain sop here on my grid that deforms the grid, like so, and if I use the points now, all my individual clones get translated, because they use the position of the points as their position. And they use the normal of the grid, or the normal of the points, as the up vector, or the orientation vector. That's why they are already oriented or rotated to match the surface normal. So the basic principle of working with clones in Houdini is to create a set of template points and then alter the template points to influence the behavior of the copy to points node. So instead of using a mountain sop, we can use a VOP to customize the effect on the template points. So create a point VOP and connect it here between the grid and the copy to points and call it effector, because that is what it does. It affects the clones. And let's color code it, maybe purple or something, like so, and dive inside. I already told you that the position of the template points directly sets the position of the copies. So if I create a constant of type vector, because points are vectors, and if I now create an add node, use the original position of my points and then add this constant to them, I can do stuff to all my clones by just altering this constant. So, for example, if I go up here with the y value, all the clones are moving up and down because the points of the grid are moving up and down. And same holds true for the other directions, like x or z. But that is still a little bit boring. What we want is individual control over the individual clones. We want to have different effects for different clones, and this can be achieved using a fall-off value. So instead of doing the same transformation to all the clones, we want to have some translated and some not. So before the effector, let's create a fall-off value, save it to the attributes of the points, and then use this attribute inside of the effector to alter the effect over our individual clones. So create another VOP, another point VOP, and call it fall-off. And I want to create a simple spherical fall-off. For creating a spherical fall-off, I need a sphere. So let's create a sphere and color the fall-off, let's say yellow, just to make sure that we understand the individual components of the system. And here we have our giant sphere. It's huge. Let's make it smaller, like for example so. And now we want to transform this sphere, because what we want to create is a fall-off value that is 1 in the middle of the sphere and then falls off to 0 when it hits the radius of the sphere. And then we want to move the sphere around and so influence the points. So let's append transform to this sphere. And if you do so, you can now hit the handle tool and you get the transformation handle and you can move the sphere around. Well, we want to create our fall-off for all our points, but we want to take this sphere into account. So connect it to the second input port of this fall-off VOP, make the fall-off VOP visible, and dive inside. Great. So here we have incoming all the points of the grid, but we don't have information about the sphere. We have to import this information, and the geometry that is connected to the second port of the VOP is coming in over this port here, op input 2. So what we can do is we can import a point attribute by using the import point attribute node. And this node expects a file, and this file is the geometry that comes in over op input 2. And then it expects a point number to sample an attribute. And here in the properties, you have to tell the node which attribute to sample. And we want to sample P, because we want the position of the sphere. There's one thing you have to know, and that is that a sphere, a primitive sphere, is actually 1 point. So if you middle click here, you see 1 point. So a primitive sphere in Houdini is composed of 1 primitive and 1 point. And that is good, because this point is actually the center of the sphere. So if we import point 0 of the sphere, we get the center. And that is great. So create a constant and set it to be an integer, because point numbers always are integers. Keep it at 0. And connect it here to pt number. Now we are importing the position of point 0 of the sphere. And here we have our points. So now what we can do is we can calculate the distance of all the points we have to the center of the sphere. The distance will be large for the points here on the outer rim and small for the points that lie exactly here at the center of the sphere. And then we can remap this distance value to create our fall-off. And this is how it works. So dive inside again, create a distance node, distance, and just connect all the individual points and as a second input the center point of the sphere. Now you get the distance between all the points and the center of the sphere. And now we can use a fit operation. A fit range operation just maps a value from one range to another range, like so. But what are the ranges we want to use? Well, let's go up for a second again and template the sphere. What we want to achieve is a value that is 1 in the center of the sphere and 0 at the radius. So we want to map our distant values such that all the values that are 0 will be 1 after the operation, and all the values that are exactly the radius should be 0, and all the values that are bigger than the radius should be 0 too. So how can we import the radius of our sphere into our attribute WOP? We can do this by using a parameter. So lay down a parameter node. A parameter node creates a parameter on the Vex object itself. So as soon as I lay down this parameter node, I get here on my interface a new parameter that float at the moment. And we call this sphere radius, because that should be the sphere radius. And suppose that this is outputting the sphere radius. It is not at the moment, it's outputting 0, but it will in the future. But for now, suppose it's already outputting the sphere radius. So then how should our fit operation look like? Well, source min means the minimum of the input range. So that is where the values are 0. Nothing changes here. But the outer maximum, the source max, should not be 1, but the sphere radius. So if I set it up like this, we get a value of 0 at the center of the sphere, and as soon as the radius is reached, we get a value of 1. But we want it the other way around, so just switch these numbers, 1 and 0. And now you get 1 as soon as the distance is 0, and 0 as soon as the distance is the radius or bigger. So that is exactly what we want. And now we can use a bind export node. And what a bind export node does is it exports a value from a WOP network to an attribute. So if I call this attribute falloff, it will be automatically created if it does not exist. Its type is float. And if I now connect this here, I get on all the points a falloff value. I can check this by going to the attribute spreadsheet, and now you see I have a falloff value. At the moment it's 0.5, and that's because this node outputs 0. Good. So the last thing we have to take into account is to transfer the sphere radius from the sphere node to this falloff node, to this parameter. Then it will be transported into the network and used. And we can do this by using an expression. Unfortunately, we don't have to write the expression. We just go here to the very first field of the radius. In Houdini, a radius is defined in all 3 directions individually or independently, but we only use the very first field. And we just say right-click, copy parameter. And now we can go to our sphere radius parameter, right-click and say paste relative references. And it will, oh, I have a spare 0 here. And what it now does is it automatically creates a channel expression referencing this parameter. And if you click on the name here, you see the result of this expression. It's 0.4 and our radius is 0.4. If I change this to 0.5, then I have 0.5 here. Great, go back to 0.4. So now this network is operational, it's functional, because now this parameter node outputs actual values, puts them in this fit node, and creates a falloff value. Cool, now we have a falloff value. Why not visualize it? Append a color node to our falloff and make it visible. And here we can say color type ramp from attribute. And that Houdini wants to know the attribute that we want to use, and that one is falloff. And as soon as I put it in here, we get a color visualization of our falloff. We can change the colors to make it even more visible. Let's say red here on the left side and blue here on the right side. And this is the range 0 to 1. And you see it works exactly as expected. In the center of the sphere, the values are 1, and at the radius, the values are 0. And if I now go to my transform node, activate the handle tool and move my sphere around, you see that the falloff value updates. So now I created a spherical falloff value that I can use inside of my effector. So now let's make the effector use the falloff value. Activate the effector and connect the color to the effector because the color is helpful. And now go inside. We have to import the attribute falloff into this network to use it. So create a bind node to bind an attribute and just state here falloff. That brings the falloff in. And now let's put something here into this constant. You see now everything is translated up by 0.5 and we want to alter this behavior. And we can do this by just multiplying the falloff with this vector. So if we put the vector into a multiply and the falloff into this multiply and then use the multiplied value here in our add node, you see the effect on the template point. Now the vector here that is used to transform the point is scaled by the falloff, and that gives us exactly the control we need. If you now make the copy to points active, you can see that we have now a falloff. And if I go to the transform and move my sphere, all the clones are going up and down with my spherical falloff. At the moment the falloff is linear. That is not very beautiful. We might want to remap the falloff values, and we can do so inside of the effector. So enter the effector again and put down a ramp node. A ramp parameter allows you to remap values. Wire the falloff into this ramp node, and the standard behavior of the ramp node is to create a color from a float, but what we want to do is to remap a float. So use a ramp type of spline ramp float and call the ramp falloff or ramp position, like so, and then wire this into the multiply. And if you're gonna up one level, you find a new parameter here on our interface of the effector called ramp pos. We can expand it, and you can see that I now have a ramp controlling my falloff. If I take this point and go down with it, you see that I can alter the behavior. And if I introduce additional points, I can smooth this out, or I can really do an S-curve. The curve is very linear at the moment. If you select the points that you want to define the spline type of, or the interpolation, then you can go to this menu here and say B-spline, and you get a smooth curve. And now I went from a linear falloff to a smooth falloff. And using this curve, I can perfectly and exactly control how the falloff curve should look. So I can do a bell curve, or I can go very sharp on this falloff, like so. It's really totally flexible. And still, if I move my sphere around, everything follows. Great, but that is only position. Wouldn't it be nice if we could control other attributes like scaling or rotation too? And we can. We have to just extend our effector. So let's go into our effector. But before we go for scale and rotation, let's do one convenience thing. Instead of using a constant here, it would be nice to have an interface element defining this translation vector. So create a parameter. And this should be a vector. And we call it position. Caps lock is on position. The string you put here into name is the internal name of the parameter, so the name that Houdini internally refers to. But you can give it a second name called label, and that is what is shown in the interface. So maybe put position with a capital P here, like so. And now connect this vector to the multiply instead of the constant. Everything goes away. That's because the default for this parameter is 0. But in a second we can change this again. Because now we have here this position parameter. And now I can go in and can just dial in whatever translation I want. And all these translations respect our falloff. One last thing is to tidy up the interface a little bit. Although these parameters are created automatically, you have influence over their layout. And you can affect the layout if you go to this little gear menu here on the Properties window and say Edit Parameter Interface. This will bring up this dialog, and here you see all the parameters that are defined on this operator. And the last two are our custom operators, ramp pause and position. And I just want to take this position parameter and move it up here by drag and drop in front of the ramp pause. Press apply and accept. And you see, now I have first the position parameter and then the ramp. I think that is clearer. Now you can dial in the position and you can alter the fall off using this ramp. Now let's scale our clones. Go back inside of the effector. To scale the clones, you have to know one thing, and that is that the template points use special attributes or attributes with special names that the copy to points understands. And if you set these attributes, the copy to points will respect them. And the attribute for scale is called scale. There are actually two attributes controlling the scale. One is called scale and the other one is called p-scale. And the difference is that p-scale is a uniform scale and scale is a vector scale that can be different in all three directions. So let's use scale because it's more flexible. So if I create a bind export and call it scale, I create a new attribute called scale. And if I now create a constant of type vector, because we want to define the scale in all three directions, and if I now switch the scale attribute to vector 2 and connect the two, everything vanishes. And that is because at the moment I'm setting a scale of 0, 0, and 0. Instead put 1, 1, 1 here, and back are our clones. If I now put 2 into the Y field, you see that everything scales to 2 in the Y direction. I can go up here, and I can go up in this direction. So you see, by just binding a vector to the scale attribute, I have control over the scale of my individual copies. But using a constant is not the optimal way. Let's do the same thing we did for position. So first create a parameter and call it scale, or sca for the internal label and scale for the external or the visible label. And then switch its type to vector. If you now go up one level, you see that I have a new parameter called scale here. Let's input 1, 1, 1 for now. And I can use this scale vector instead of my constant. And everything goes back to scale of 1, 1, 1. So now I can control this here from the interface. To take our fall off into account, I do the same thing as with position. I multiply the fall off with my scale vector that's coming from the interface, like so, and use this instead. And you see, immediately I get the effect of the fall off. So everything is 1 where the fall off is 1, and where the fall off is 0, everything vanishes. But that is not the behavior I intend, because I want to change the scale instead of absolutely setting it. So the values that I input into my interface element should alter the scale. And that can be achieved if I reintroduce my constant and switch it to vector and set this constant to be 1, 1, 1. 1, 1, 1. So that is the unit scale. Nothing changes if I use that. And now I want to add my values here that I define over the interface to this constant. So I take the vector, the scale vector, multiply it by the fall off, and then add it to 1. And if I do this, now all the individual clones stay at a scale of 1, but the ones that have a fall off of 1 are getting bigger. So now I have a more flexible behavior, because if I just say 0, 0, 0, I introduce no change to the scale. If I go negative, I can make stuff smaller, as you can see here. And if I go positive, I can make stuff bigger. And that is probably better than setting the scale absolutely. And still, if I move my fall-off around, now everything is moving and scaling. So what's missing is to introduce another ramp to have more control over the fall-off of the scale. So introduce another ramp parameter, switch it to spline ramp, call it ramp scale, and wire it up here between the fall-off value and the multiply. And now I have a second ramp here, ramp scale, and that can be used to control the scale fall-off. So now I have individual control over the fall-off of the position and the fall-off of the scale, which is cool, because now I can dial in even more complicated effects. So let's say we go here to a value of 10 and here to a value of 10, or maybe in this direction, like so, and we are creating little planks from our clones with our fall-off. And let's switch this fall-off to B-spline 2, like so, that it's smooth. And we can now alter this fall-off to have a peak here. And you see now everything immediately scales up very quickly, but the position changes more smoothly. Let's exaggerate this effect like so. And you see, you really have a lot of control over the effect. Or maybe let's even go down with the scale again, like so. So stuff scales up and is transformed up and then down again, like so, for example. Maybe let's go down with the translation a little bit. And now we have a neat little motion graphics effect. Okay, now what's missing is rotation. So back into the effector. First, let's tidy up a bit. So here is the output for the position. Here's the parameter for the position. The add, switch the spline type by pressing Shift S. I think this is a little bit more clear. And now just rearrange your nodes such that everything is a little more tidy, like so. Okay, now let's add rotation. It's the same story again. First we need a parameter for rotation. So create another parameter and call this one rot, and for the label rotation. Like so. It will be a vector too, because we want to define the rotation in all three directions, or for all three Euler angles. And now what we want to do is we want to mix the rotation with a rotation of 0. So the rotation that comes in should be mixed with the rotation that is already there. The mix node is just doing a linear combination. It's just finding the average value between the two inputs by using the bias. And the bias is between 0 and 1. So create a constant. And let's say that this constant is a vector. And the vector is just 0. And now we can mix between this constant here and our rotation that's incoming from the interface by using the fall-off. Like so. The attribute that Houdini is using to define the orientation is called orient, and it is a quaternion. A quaternion is quite a complicated thing because it's a 4-dimensional vector. But the math behind quaternions is not necessary for you to use them. It's enough if you understand that a quaternion is encoding a vector, so an axis, and a rotation angle around this axis. Because these two informations are enough to define the 3D rotation. And fortunately, Houdini has nodes that deal with all the hairy math. And one of these nodes is Euler to quaternion. What this does is it takes in a vector of Euler angles, so heading, pitch, bank, and creates a quaternion that represents exactly this rotation. So if we now connect this mix to the rod port of our Euler to quaternion, we create a quaternion. So now let's bind export this output here to a new template point attribute called orient. And that is a special attribute too that the copy to points knows how to deal with, and it is of type float4, vector4. That is a quaternion indicated here by this neon color. And now you can connect it here, and the orientation immediately changes. And that is because the orientation was actually present before. And that is due to the presence of the normals here. Because the orientation is defined in a hierarchical order. If an orient attribute is present on the geometry, Houdini will use the orient attribute. But if the orient attribute is missing, it will use the normals of the points. If the points have normals, it will use these points to orient the individual clones. But because the normal is just a three-dimensional vector, this is not as precise because it is defining the general direction, but it is not defining the twist around this direction. The orient instead does exactly this. So now I have another interface element called rotation, and in here I can change the rotation. One problem is that the values I put in here are in radians. Radians are used to define rotations mathematically, and they are running between 0 and 2 pi, 2 pi being 360 degrees. But working with degrees is so much easier for humans, at least for me. So let's do one last thing and convert the input of this parameter to radians. So let's lay down a degree to radians node. And that means that instead of treating the input directly as radians, it will read the input, and if it finds 360, for example, it will convert it to 2 pi, so 2 radians. And if I now connect this, I have now control here where I can say 180, and it will rotate exactly 180 degrees. So for now, let's eliminate all the other effects just to be able to see what the rotation thing is doing. Maybe let's scale a little bit in one direction, like so. And you see, now we have a rotation. And if I move my fall off, the clones are happily rotating 180 degrees. I can do more. If I go in here, I can do 360 and I get more rotation. And if I slowly move my sphere, the individual clones rotating, especially here at the border, it gets very apparent how they are rotating as soon as I move my effector here. Okay, that is the rotation. What's missing is another ramp, because we want to control the fall off for the rotation too. Let's call this ramp rotation. Again, it's a spline ramp. And let's put it here between the fall off and the bias. And this ramp will be used to control the distribution of the rotation. Now I can do the remapping of the fall off for all three components: position, scale, and rotation. And that already gives me a quite versatile system, because now I can change the radius of my sphere, I can move the sphere around, up and down, left and right, and I can dial in different effects that this fall off should have. Like for example so. And now I have a pretty basic but nice motion graphics effect. So to conclude this first part of the tutorial about clones, let's add a technique we learned last time. Let's warp the input space of the fall-off to make the fall-off edge more interesting, because at the moment the edge is just round because it's a spherical fall-off. But this is computed from the position of the points. And what we can do is we can use noise to warp this position before the distance is computed. So if we lay down a turbulent noise that you know from last time, switch it to original Perlin, and the signature to 3D noise, I generate noise vectors if I connect the positions here. And now I can add these noise vectors to my points. And by doing so, I move my points around. I transform my incoming points by the noise vectors. And if I now use this as the input of our distance function, I get a noisy edge to my fall-off. Because the input space is not linear anymore, or not ordered anymore, but warped by noise. And by using the amplitude of this noise, I can dial in the effect, or I can control the strength of the effect. And that is really making things a lot more interesting, because now I can do a noisy edge on my fall-off. So with this in place, I now have a system that is already quite nice, because it allows me to do interesting clone effects with a noisy fall-off and with control over what exactly is happening and the ramps and stuff like that. So growth effects and creation effects are perfectly possible by doing this. Next time I will go into more detail about what can be done with MoGraph setups like this one. I will show you how to implement a linear fall-off and then arbitrary fall-offs, and then we will talk about relaxing points to deal with intersections and stuff like that. Although I'm pretty sure that you enjoy coding in VOPs as much as I do, maybe you just want to use a MoGraph system without coding and without building your own setup. And the good news is, since yesterday you can, because Moritz of Intagma and Henry, known as Toadstorm on the forums, decided to implement a motion graphic system into Houdini called MOPS. And you can go to this webpage here, motionoperators.com, and just download it on GitHub for free and try it out yourself. It has all the nodes necessary to create motion graphic clone-like effects. So check this out and stay tuned for the next episode. I hope you learned something today, and see you next time.